This diagram compares a traditional normal distribution curve on the left with a flattened distribution featuring heavy tail risk on the right. For decades, quantitative risk managers relied on backward-looking metrics like value at risk, a calculation measuring the potential financial loss within a firm over a specific time horizon based on the bell curve on the left. The 2026 SCR exam requires candidates to recognize that this historical approach systematically fails when applied to climate risk. Historical normal distribution models assume that variables remain stationary over time. They operate on the premise that past data reliably predicts future outcomes, confining the vast majority of probability strictly to the center of the curve. Physical climate systems and transition policies are nonlinear. Structural environmental shifts continually push probability into the extreme right side of the distribution. This inflates the fat tails, generating statistically unprecedented outlier events that do not exist in the historical dataset. Because the past no longer bounds the future, backward-looking models break down. Accurately quantifying these massive physical impacts requires a methodology that strictly projects forward. To master the SCR exam, you must discard the assumption that historical time series data can prize modern climate exposure. The required approach relies entirely on forward-looking scenario modeling. The first step in this modeling is properly categorizing the threat. Climate risk does not sit on a balance sheet as an isolated, standalone category. Instead, it functions as a driver. It is an external variable that feeds into and amplifies pre-existing traditional financial risks, like credit, market, and operational risk. This matrix visualizes the exact mechanical pathway you must master, the climate risk transmission channel. It acts as the logical bridge translating climate science directly into financial ledgers. The architecture is strictly sequential. An environmental shock begins on the left as a risk driver, travels through the center transmission channels, and emerges on the right as a quantifiable financial risk. Your primary objective on the exam is tracing a single unit of risk from left to right across this entire matrix. Understanding this sequential translation separates superficial ESG reporting from rigorous, professional quantitative risk management. Looking at the first column, we identified initial inputs. All climate financial shocks originate from two variables, physical or transition risk. Physical risk branches into two categories: acute risks, sudden weather anomalies, and chronic risks, gradual shifts. On the exam, you will encounter acute physical shocks modeled as unpredictable, high-severity events, such as a localized spike in Category 5 hurricanes or sudden catastrophic inland flooding destroying regional infrastructure. Conversely, chronic physical risks are modeled as slow-moving, irreversible baseline trends. These include progressive sea level rise encroaching on coastal real estate or sustained agricultural heat stress degrading crop yields year over year. Transition risk is driven by the global economic shift toward a low-carbon economy. It expands into three primary channels: policy, technology, and market sentiment. Transition shocks often materialize as sudden policy mandates, like the imposition of aggressive carbon taxes, or as technological leaps, such as utility-scale renewables rapidly undercutting the unit economics of fossil fuels. Beyond direct policy and technology, overarching shifts in market sentiment trigger a rapid repricing of carbon-intensive portfolios as capital abruptly reallocates towards green infrastructure. Every legitimate climate risk analysis begins by isolating and accurately quantifying the severity of one or both of these dual drivers. Because it is impossible to predict the exact regulatory or technological turning points of the next 3 decades, risk modelers must stress-test portfolios using standardized scenario analysis. This multi-axis graph illustrates the NGFS framework. The NGFS is a coalition of central banks defining standard climate scenarios. Over a 30-year timeline, it maps the divergent trajectories of physical and transition risks. Under an orderly transition scenario, immediate climate policy is enacted. The yellow transition risk line spikes early as markets absorb decarbonization costs, which successfully keeps the blue physical risk line flat over 30 years. Under a hothouse world scenario, policy action is delayed. The yellow transition risk stays low initially. However, this inaction ensures the blue physical risk curve scales exponentially into severe territory in later decades. These curves demonstrate a strict inverse mathematical correlation. Implementing aggressive climate policy today mitigates long-term physical damage, but it induces immediate short-term transition shocks across the market. Delaying policy intervention suppresses those immediate transition costs, but mathematically ensures compounding physical damages to global assets in the future. Selecting the correct NGFS scenario pathway forms the foundational baseline assumption that dictates the trajectory of all subsequent financial modeling. Once the macro scenario is established, the analysis moves to the second stage, the microeconomic transmission channel. Here, we map the macro shock down to a specific corporate entity. Consider an acute physical shock, like severe flooding, directly striking this coastal manufacturing facility. This physical event instantly transmits into the facility's corporate financial statements, striking the balance sheet and the income statement. On the balance sheet, the direct physical destruction of the plant and inventory causes an instant, calculable devaluation of the firm's tangible assets. Simultaneously, the income statement absorbs the effects of business interruption. The firm experiences an unpredicted spike in operating and repair costs precisely as its revenue streams plummet due to halted production. This conversion is the critical translation leap. You are taking raw geophysical weather data and converting it into standard depreciating corporate accounting figures. Climate science remains theoretical to a risk manager until it mathematically impacts a specific entity's cash flow and asset valuation. The final stage of the framework converts this degraded corporate accounting data into strict, quantifiable financial risk metrics. Within the credit risk node, modelers isolate two fundamental mathematical components. First is probability of default, or PD, which is the likelihood the firm will miss debt payments. Second is loss given default, or LGD, the percentage of total exposure a lender loses. Plummeting revenue and spiked costs mathematically degrade the debt service coverage ratio, driving up probability of default. Simultaneously, the facility's physical destruction devalues the underlying collateral, mathematically increasing loss given default. This same left-to-right transmission logic must also be applied to calculate market risk through equity repricing and operational risk by modeling supply chain failures. By strictly following this mechanical sequence, risk modelers take a macroeconomic climate variable and produce a specific, quantifiable credit downgrade. Deriving precise PD and LGD outputs from raw climate data inputs is the absolute threshold for passing the quantitative portions of the SCR exam. Internal quantitative modeling serves external corporate reporting mandates. This integration relies on frameworks like the ISSB, the International Sustainability Standards Board, and the TCFD, the Task Force on Climate-Related Financial Disclosures. Modern regulators explicitly demand proof of this mathematical transmission modeling. They reject generic qualitative corporate sustainability statements in favor of verifiable financial impacts. This matrix shows 4 ISSB pillars: governance, strategy, risk management, and metrics, overlaying our transmission model. NGFS scenario pathways fulfill the strategy pillar, proving the firm is stress testing future timelines. Calculating probability of default and loss given default satisfies the strict metrics and targets requirements. Executing this rigorous transmission modeling is the only legally defensible way to differentiate compliant corporate disclosure from subjective greenwashing. The SCR exam charts a continuous journey from a macro-environmental anomaly at the start to a highly regulated microfinancial reality at the end. Remember the core thesis. Traditional historical data models are effectively obsolete for pricing the nonlinear reality of modern climate exposure. Candidates must continuously practice tracing the inverse time horizon dynamics of physical versus transition risks across different portfolios and NGFS scenarios. Passing the 2026 SCR exam requires stripping away the politics and viewing every climate event strictly through the lens of how it mathematically amplifies traditional finance. Mastering the mechanics of this forward-looking transmission framework establishes the quantitative rigor required of a certified climate risk professional.